My name is Kirill Alabin, and I want to present you the study of our group, which name is the study of possibility of initiating tungsten alpha decay using the electric explosion. So I start with the slightly history introduction. Our idea lies in experiment of Garrett Vent and Clarence Iron. These two American scientists made their experiment in early 20s of last century, and the idea was based on several facts firmly established to that time. Firstly, there are no characteristic optical spectral line of heavy elements in the spectrum of stars and sun, of course. And of course, to that time, the temperature of the sun surface was measured carefully. It was about 6,000 degrees Kelvin, and also not far ago from that time, experiment of Anderson showed that the temperature of plasma, which generated in the electric explosion of conductors, thereafter I'll refer to it as a EEC, the temperature of plasma obtained at that moment was about 20,000 degrees of Kelvin. So, based on these facts, they decided that maybe the heavy chemical elements are unstable at these temperatures. And again, at 1919, Rutherford showed that using heavy energy alpha particles, he obtained nuclear reactions in laboratory conditions and showed that it's generally possible to do this. So they decided to test this one. Oh, of course, the electrical circuit of their experimental setup is quite easy. It's only circuit that charges capacitor battery, which capacitance is about 1 microfarad, and it discharges from through the gap into the wire, thereby heating it to about 20,000 degrees Kelvin. So the explosion chamber was like that, spherical bulb made up with quartz glass. 2 electrodes was inserted in it, sealed in it from 2 opposite sides, and the wire is located as a spacer between them. Another electrode is sealed in equatorial cross-section compared to this one, to these 2. It was used as for the ignition of plasma to study the chemical composition of gas, because to that time solid-state mass spectrometry wasn't even made. So the only method they can use is optical spectrometry. So what they obtained, the volume of gas generated after the electric explosion was about 1 cubic centimeters, average over 21 experiment, and of course under normal condition. And it's about 10 power 19 particles. Also, they states that the gas optical analysis of gas showed the presence of characteristic bright yellow lines of helium. Also, important thing to mention, the spectral analysis did not show any characteristic lights of hydrogen, which is a really important thing, because getting rid of water vapor and of course in turn of hydrogen from the vacuum system, it's really a complicated task. Also, they observed several spectral lines, but were unable to decipher them, it was 2 lines in the red part of spectrum, the bright line in the blue part, and the pale purple line. In several experiments, they also observed 2 yellow lines. So maybe today their idea seems deeply flawed, but considering the carefulness with which they made their experiment, we decided to test it. For past decades, for past century, electric explosion of wires studied very carefully, but today generally accepted opinion in physics said that in high temperature plasma only fusion nuclear reaction can occur. For example, deuterium plus deuterium. So the main idea of all these studies with electric explosion was to see neutron flux and X-ray radiation. And because nobody ever reported of spectrum of helium or even studying of composition of gas, it seems like there is no effect there. But in our turn, in other hand, we did not manage to find any observation of gas formed after electric explosion at all. So probably this is the reason. So to test it, we made our setup, which is shown on this slide with some diagnostics, and I'll present it. So the main circuit of our system is simplified here. Almost the same as in iron and vent experiment. The only difference we made is the explosion chamber, which is made of quartz cylinder sealed with 2 flanges on the bottom and top. And of course we used not only quartz cylinders, we used also stainless steel cylinder. I maybe tell you about why we use it later. The volume of our explosion chamber, our cylinder, was about 250 cubic centimeters. And the whole volume of all system until the sealing gates with all technical appendigates was about 394 plus minus 4 cubic centimeters. This value is very important because for precise measuring of particles in your chamber, you need to know volume very carefully. Our electric parameters of setup was almost equal to those in iron and vent experiments, so everything else is the same. Because every study of electric explosion was conducted in really big setups with a lot of wires, with great volume of explosion chambers, the main idea of these studies was to explode wires and without sealing it off from the pumping station. And because our interest was in studying the gas formed after this explosion, we need to make some changes in these preparations. So our chamber is cut off from pumping station right before the explosion. The time interval between these 2 steps is about 10 seconds. And of course, as iron and vent experiment, we also cleaned our chamber with glowing discharge and degassing the wire to get rid of gas dissolved in this wire. Overall, explosion you can see here. This is this is the frames obtained through using high-speed video camera, and this is 3-frame photo to see the uniformity of distribution of plasma along the wire lengths and the appearance of so-called hot spots in it. So our diagnostic methods can be divided into 4 great parts. Firstly, it's electrical diagnostics, photorecording diagnostics, optical diagnostics, and gas diagnostics. Electrical diagnostic consists of Rogowski coil, voltage divider, and current loops, which is quite common methods in such type of experiments, so I won't stop on them at all. Photo recording diagnostics consists of high-speed video camera, which helped us to explore the explosion overall, its dynamics. And another system is three-frame photo recording systems, which consist of image intensifier tubes with some optics. The time of exposure of such tubes, image intensifier tubes, was about 15 nanoseconds, so we can obtain really fast frames. Optical diagnostics was used to determine the chemical composition of gas using spectrometry, of course, and another diagnostic is integral light intensity, which was used to see dynamics of light during the explosion. These two spectrometers differ in optical resolution, of course. One of them uses prism as the dispersing element and has really low spectral resolution, but spectral efficiency, optical spectral efficiency is really great. And we obtain through it overall spectrum. And other one uses diffraction gratings, which gives him a really great resolution, but its optical efficiency really low, so we can obtain some results only when light fluxes are really great. And gas diagnostics helped us to, again, see the chemical composition of gas formed there. We control, of course, the pressure in chamber before the explosion, during the explosion, and after the explosion. Time of flight mass spectrometer used to measure the composition and also gives us quantitative measurements of this composition. And helium leak detector, this is our know-how. We used it as a measurement tool, but on this measurement I dwell in details slightly later. So what the results? Experimental results showed that pressure surge after the explosion was about 50 pascals, and gas consists of about 40% hydrogen, and the remaining 60% is the gas mixture that's similar to air. The reason for such a great amount of hydrogen is probably hard to determine, but we can say that most of this hydrogen probably formed because of the water vapor still present in the chamber. As you can see, the peaks of M equal to 2 atomic mass unit and M equal to 28 atomic mass unit are prevalent in this spectrum. Of course, the M2 is refers to hydrogen molecule, and M equal to 28, probably the mixture of nitrogen and carbon monoxide. To this, the peaks of other peaks are the water vapor and its fragments, M equal to 80, 70, 16, and so on. Because it's hard to get rid of water in your vacuum system, really. Another interesting thing is that we obtained the M with 3 atomic mass unit. In those, the first picture, it's really hard to see, but here is the magnified part of this spectrum. Well, due to the fact that our mass spectrometer, MS200, has low spectral resolution, it can, this peak may interpret it as a helium deuterium molecule, of course, the hydrogen ion, the hydrogen isotope tritium, and the helium isotope helium-3. Well, the presence of tritium in our experiment is rather low. The probability of it is rather low because we didn't obtain any significant amount of radiation. Also, it's really hard to make a connection between this peak and the hydrogen ion because the time of life of such ions is really small compared to the time of measurement, and the chances of formation of such ions in ionization part of a mass spectrometer is neglectable. So we can say that this peak can be referred as hydrogen deuterium molecule or helium-3. If this is hydrogen deuterium molecule, then probably the ratio between peak of m equal to 2, peak equal to m3 should be in a ratio equal for the hydrogen deuterium found in nature, which is about 3,500 to 1. But the ratio obtained in our experiment was about from 30 to 1 to 2,000 to 1, so it's really different. Again, if this peak referred to hydrogen deuterium molecule, then the time dependence of this peak should be equal, should be correlated between each other. But as you can see, we can measure it through time, and the time dependence is rather differently. So because our time of flight mass spectrometer didn't see any particles with m equal to 4, helium of course, or maybe deuterium molecule, we decided to use other measurement procedure to calculate the particles with this mass. For this purpose we used helium leak detector, and of course if you use some detecting tool as a measurement procedure, you need to calibrate it. This helium leak detector is just another mass spectrometer calibrated only to feel m mass equal to 4 atomic mass unit. So and it can feel this mass even from the air, which is really great. It's really great sensitivity. It has really great sensitivity. So before we can use it as a measurement tool, we need to calibrate it, of course. We did it. We did a lot of test experiments with gas medium, which with known chemical composition, which was air, of course. It's easy to use it. And we obtained results showed here, which show that result measured with the helium leak detector was almost equal to the theoretical calculated number. Of course, if you know, I need to mention that helium leak detector was measuring flow rate. But knowing the volume of a chamber and pressure, you can easily calculate the number of particles. So after we calibrate it, we can use it as a measurement procedure, and the procedure was as follows. After the electric explosion, we pump all gas formed in chamber through this leak detector and measure the number of particles. After the several hours, after that, we seal off our chamber. For several hours after that, the pressure in chamber grew due to the diffusion of gas from the walls and from leakage of air from the atmosphere. And after several hours, we repeat this procedure. So we obtained really strange results. The number of particles measured directly after electric explosion was smaller compared to the number of particles measured after several hours. So we decided to continue this measurement, and we continued for about 200 hours. And we saw that after 70 hours, the number of particles formed in such measurement becomes constant and determined only by leakage of air through the ceilings. And our idea why this value works so strange is that helium atoms formed during the electric explosion are hammered into the surface of a quartz cylinder and slowly diffuse after a certain time. So to be sure that this idea is really what it is, we decided to test to make test experiment with iron wire, for which isotopes of iron is really stable, and the process of alpha decay of them is energetically unfavorable and prohibited for this. So, as you can see in this slide, the value measured for iron wire was almost the same as the value for the air. As you can see, it's almost the same values. And for tungsten wire, this value was at least one order bigger. Oh, sorry. Okay. But because helium leak detector has really low resolution on masses, we was always, yes? Oh. But as I remember, next is also my, yes, and I can take. So, because the uncertainty we obtained from the results of helium leak detector, because its resolution on mass is really low, we cannot really be sure if it measure deuterium molecule or helium atom, so we need to also obtain the optical spectrum of helium to be sure. And for that purpose, we used our optical measurements. Firstly, our optical measurement was optical monochromator for obtaining the overall panoramic spectrum of plasma formed during the electric discharge. And the brightest line in examined spectra was, of course, hydrogen atomic line, and several other lines that we cannot register with, we cannot identify with this methodics. But as a rule, the panoramic spectrum was the combination of discrete and continuous spectrum. The continuum spectrum was practically absent at the small wire diameters, and at large wire diameters, the continuum spectrum was so intense that you cannot say anything about discrete part of the spectrum. And when we studied the time behavior of integral light, we saw that, again, a really strange result, that for the wires with diameter larger than 100 micrometers, the radiation intensity has two maxima, and the maximum intensity of second peak occurs at about 200 microseconds after the discharge. By that time, the capacitor bank was almost all discharged, so this behavior seems very unexpected. But comparing this result with the result of panoramic spectrum, we can say that the first maxima probably associated with the discrete spectrum, and the second maximum probably associated with the continuous spectrum. But still, we has no idea why we have two maxima in the light intensity. This result is very easily to reproduce, and it was obtained in every electric explosion of wires, so you can try to replicate it. Using our second optical spectrometer, we were able to register other lines and identify them. That was sodium doublet in yellow part of spectrum, oxygen atomic line, and carbon ion lines. Comparing this result with the result of iron and vent, we can say that probably it's those lines they were saw in their experiment and were unable to decipher. Another thing we want to obtain optical spectrum of helium, but it was really hard to do that. We don't know why. So we decided to test one thing. As our mass spectrometer showed that a lot of hydrogen formed in the gas after electric explosion, and again our helium leak detector detects mass equal to 4, we thought that maybe we should investigate the emission of helium on the concentration of hydrogen. I show you what I mean. Well, we tried to make different ratios of helium to hydrogen mediums in our explosion chamber and try to excite it with the high energy pulse in this chamber. And we saw that with the concentration of helium to hydrogen for about 1 to 20, the helium line equal to 6678 almost barely visible. And with the ratio of helium to hydrogen 1 to 50, these two lines are stop to radiate at all. And the strong hydrogen atomic line appears. So, because of that, we thought that without lowering the partial pressure of hydrogen in our gas medium, we cannot obtain optical spectrum probably. So our investigations showed that after several hours, the number of particles with m equal to 4 atomic units are much greater, or at least 1 order greater than after the electric explosion. And because all gas pumped through the leak detector at first measurement, the helium or the hydrogen are not present after this first measurement. So in such condition, we decided to try to excite plasma and see its optical spectrum. And of course, we excited and see 2 optical lines of helium in such conditions. And using slightly different regime of our setup, a periodic regime with lower Q value of circuit, we also changed the partial pressure of hydrogen formed after electric explosion and were able to obtain helium lines directly at the moment of electric explosion. So what are the conclusions? The amount of gas formed after electric explosion of tungsten wire was about 10 power 18, 10 power 19 atoms. And it's correlates very well with the result of iron and vent experiment. Despite all measures, we cannot really fully purge hydrogen from our system, and it's significantly complicated our diagnosis of helium. In some experiment, the presence of particles with m equal to 3 atomic mass unit was measured with confidence, and our results showed that probably it could be helium-3, which correlates with the result of iron and N, because helium optical spectrum, helium-3 and helium-4 optical spectrum are almost the same, but it contradicts really great with our theoretical concepts. Probably they are not good, maybe we change something. The presence of atoms with mass equal to 4 atomic mass units was reliably detected, but based on our results, it's it is impossible to be sure that this is the helium atoms, but some data show that probably this is the heliums present in the mixture. Contrary to our expectation, the highest number of M4 particles obtained not directly after the electric explosion, but after a certain time, after 3 hours. Several bright lines in red part of optical spectrum were observed, and they were identified, and probably this is the same lines that Iron and Wendt found in their experiments. No fast neutrons and other radiation were observed during this electric explosion. So, considering these conclusions, we can say that we replicate Iron and Wendt experiment really carefully. We can say that probably there is alpha decay of a tungsten during this process, but if you want to say that there is low energy nuclear reaction there, you need to carefully measure the daughter nuclei and to find the energetical balance of these reactions. So it's the other study, probably. Thank you for your attention.